2009. Initially, he worked as an FPGA developer and a developer of low-level software in timing and safety-critical systems. Later, he transitioned into risk management and quality assurance, and currently he is a senior system engineer and project manager in the area of medical devices and heavy ion therapy systems. Luca, it's such a pleasure to have you here with us. Thank you for taking time from your busy schedule and offering to deliver a lecture on this very interesting topic. I give you the floor. And in the meantime, we will also have Christian Kuar, who will support Luca with delivering part of the presentation. I'll leave it up to Luca to present and to prompt him. Thank you.
Thank you so much, Nicholas. Thank you for the introduction. It's also a pleasure to be here and presenting our lecture. So hello, everyone. I hope you were able to grab something to eat and have enough energy to attend the rest of the lectures today. So let me start my screen sharing. If you can just confirm, can you see the presentation?
Yes, we can.
All right, perfect. Thank you very much. So today, Christian and myself will give you an overview of Hadron therapy control systems. We will make also a short demo, a live demonstration, which I hope will be interesting, not just to see the slides, but also something happening. So let's dive into it. So we plan to have around 45 minutes of the lecture itself, including in that time is about 15 minutes of the demonstration, and then we leave about 15 minutes for the questions. So we'll say a few words about COSYLAB, about our company. Then we will define a bit what Hadron therapy control systems are or what they represent. We will take a look at some of the technical aspects of the architecture of such systems, how this software looks like, how it's visualized, how we design it. We will talk about the importance of having and using simulators while developing these systems and testing them. Then follows a around 15-minute demonstration. Christian will guide us through a clinical workflow, a typical workflow that is used when treating a patient using typically a proton therapy machine. Then we will see what kind of technologies and programming languages we use in this kind of software, what is the life cycle that we take during development, and then lastly, what kind of team, different roles, experiences, and how much time do we need actually to develop such systems. Good, let's start. So COSYLAB, we're a company based in Slovenia, but otherwise we also have quite a few subsidiaries around the world, in particular in China, United States, South Korea, Ukraine, Switzerland, Sweden, and France. We work in 3 different areas. One is big science. This is where the company was founded in 2001. We started working for developing control systems for particle accelerators, for radio telescopes, optical telescopes, fusion reactors. Then about maybe 13 years ago, we started working in medical particle therapy systems. So this is what the focus of today's lecture will be. So taking a look at a control system for a particle therapy system. And then we also design and develop medical devices, which can be used either in intensive care units or in vitro diagnostic devices and similar. Currently, we're about 350 people, I think, already in total with all the subsidiaries together. We're very proud of having that most of us are engineers, so it's really an engineering company, and we also have quite a few PhDs from different areas. So thank you, Nicholas, already for introducing me. Also a little bit about Christian. Christian, he's a physicist. He graduated from the Faculty of Physics and Mathematics in Ljubljana, Slovenia. He has joined COSYLAB in 2014. First started as a developer, and then later on became a senior and a lead developer, also a senior architect. Good. Yeah, let's go a little bit to the basics. So whenever in this lecture, I will talk about hadron therapy. I also kind of interchange it with particle therapy. And when we design these control systems and when they're finally installed and used, it's mostly in proton therapy machines, because these are the most widespread currently in the world and in clinical use. There are a few carbon ion machines, like the one in Austria, Mid-Austron. So kind of hadron therapy, particle therapy, but mostly it's proton therapy machines where this software is running nowadays. When I say control system, some people might immediately think about some control loops, maybe some regulation loops, but here we mean this in a more broader sense. So this is kind of a software or a set of software which is used to control different devices in a desired way, and also provides a user interface to the operator. Typically, this is a radiotherapy technician, an RTT, who uses this software to control the whole treatment. Now, about this lecture, it's titled Hadron Therapy Control System. So what's so interesting or special about hadron therapy? So particle therapy devices, medical devices, I think I could claim that they are probably the most complex medical devices in the world. So what this means is that they contain a few tens of devices or a few hundreds of different devices. So power supplies, ionization chambers, you have a robot, you have an imaging system, you have different kind of motion systems. So controlling all these devices becomes quite a complex problem. So that's why a hadron therapy control system needs to be able to handle this complexity of so many different devices and working in different time domains. So some of them need really precise control in the nanosecond range, like the timing, exact timing of the accelerator or synchrotron ring, for example. On the other hand, some other devices are fine with millisecond range, some power supplies, setting the current and so on. These machines or medical devices at the end are very expensive, typically a few tens of millions of euros. So a hospital really wants to treat as many patients as possible. So on one side, to get the benefit of having patients treated with particles, but also they want to be able to recuperate the cost of the device as much as possible. So our control system here should not introduce unnecessary overhead and delays in the treatment. So we also have to be careful that all the steps in the treatment are as efficient as possible. And since it's a medical device, really safety is #1 priority. Safety of the patient, safety of the users, of people around the device. So when developing this software, this is really an important factor that influences how we develop it and how we test it. Just an honorable mention. So what about conventional radiotherapy, or maybe the newest type of boron neutron capture therapy? Are control systems for these two types of therapy devices similar? Yeah, in fact they are. So architecture is very similar. The difference is just then in the number of devices. So it might be scaled down, for example, for radiotherapy LINAC. So it's simpler, while for BNCT it's quite the same as for proton therapy or carbon therapy. Okay, now first, let's call it a technical diagram. So this is a typical architecture split into different layers, or we call them tiers. So this is kind of a 3-tier architecture. And what I just want to show you in this diagram is that depending on what kind of time domain you work in, there are different requirements or restrictions. So for example, if you want to control the devices which are on the lowest tier or lowest layer, we call this also a hardware abstraction layer, then typically you work in shorter time domains, or the time is stricter. So here the code or the software has to work in real time, has to be more deterministic. When we go up through the tiers, when implementing this clinical workflow, all the logic behind the GUI, the graphical user interface, the timing requirements are not as strict. You may even come into the seconds range, roughly speaking, because you have a human interacting with the software. but then the complexity of the logic becomes bigger. So typically, yeah, the higher you are, less performance requirements there are, but there's more logic. But the lower you are, there's typically less logic, but you have to work in a more stricter time domain. Okay, now we come to a typical overview. So this is an image that we very often take a look, when we deal with either a new type of therapy machine, or we talk with different hospitals or companies developing these systems. This is typically what we put on either a shared screen on a whiteboard, and then we start discussing, who is doing what, who is developing this system, who is doing the other one. So here, we just enable this pen functionality. So this is what we typically call a Hadron therapy control system. This is a set of components or subsystems that are part of the particle therapy machine, while the ones at the top are part of the hospital information system. So you do, of course, need a treatment planning system, oncology information system, and PACS to prepare the treatment plan. But then when the patient, comes into the treatment room, then the systems below are the ones responsible for carrying out the treatment. So in today's presentation, we will mostly focus on TCS. This is kind of a generic term used in the industry. So this is a treatment control system. This is the main software that also has a GUI here, so graphical user interface. This is the part where the RTT, or radiotherapy technician, works with, and they would open the treatment session here. They would see which patient is scheduled for a certain time, what kind of treatment will they deliver to that patient. They will monitor the delivery of the treatment, and then finally close the session. So this will be the focus of our presentation, and also when Christian will give a demonstration, we will see how this works. And then what TCS, or treatment control system, does as well is it has to communicate with real hardware, with real devices. So then we have accelerator, we have the beamline, we have a dose delivery system, which typically this is a pencil beam scanning system. Then you might have either a 2D X-ray system or CBCT imaging system in the room. You have to also be able to control it and communicate with it. And there are typically numerous devices that also move inside the room. So a robotic couch, the gantry rotating around the patient, imaging devices might retract and move around. So all of this has to be under control. Good. Okay, now the scary slides, or the scary diagrams. So if I go back a little bit, I have a few slides that will show a zoomed in overview of TCS. So I will not go into details there, but I just want to give you an impression or understanding how complex TCS is. So on this slide is just one box, so one green box, but when you open it and look inside of it, there are additional boxes, additional components, units, adapters that are inside of it. So just to give you a perspective that there's quite a lot more that's hiding beneath it. And then if you would zoom in a little bit more, you would see then additional components within those ones in TCS. So for example, here's the one allocation component. This one is responsible for allocating the beam in a multi-room facility. So if you have more than one treatment room, if you have 2, 3, or 4 treatment rooms, you typically still have just one particle accelerator. So you want to be able to schedule the beam, or kind of reserve the beam and allocate it to the room that is currently being in use. So there's only one room that can use it at a time. So the allocation component will make sure that the correct room will get the beam, and others then have to wait. But they are typically then preparing the patient still, or moving the patient out of the room. A few more components. So clinical component, this one gets the treatment plan from the college information system. It gives back the treatment report at the end. Delivery component would communicate with the pencil beam scanning system. It would request the beam from the accelerator at a certain energy. You might also notice, okay, the text is quite small, but you might see that there are a few boxes that say adapt or adapter. And these boxes make sure that whatever hardware that you have at the end, which might be from different manufacturers. So one hospital might have a robot from one manufacturer, while the other hospital decides for a different manufacturer. So what we would do when we kind of integrate this kind of TCS for a particular hospital, we would ask them, okay, which kind of robot do you have? And then we would adapt or modify only the adapter so that we can communicate with that robot, while the other parts would typically remain then unchanged, so that you don't need to change all the software, all the code, but just the adapter at the end. Okay. Two more components. So motion component, already talked about moving the robotic couch. You have 6 axes that you have to move around the room. You might have an imaging ring that has to move around. You might even have the nozzle or the snout that retracts and expands or extracts out. And then you have the GUI component. So the interface to the user, you have to provide the user all the information, what's happening with the patient, how much dose has been delivered, what are the coordinates of the robot. And on the other hand, get the inputs from the RTT. So when they enter the commands or click around, you have to, of course, take these commands into account. Okay. This is all from the diagrams, so no more details. Now I'll say a few words about simulators. You can imagine that a particle accelerator or a robot, or then even a CBCT ring are on one side very expensive, on the other side very heavy and big devices. So we simply cannot have them in our offices and run them and test with them. So typically, these devices are available only at the end in the hospital, or sometimes they are available in a test facility for a short amount of time. So it's really important that we have simulators. And so basically, we develop software that behaves or communicates in exactly the same way as a real device would. So this then gives us the ability that multiple developers, so multiple team members can use these simulators on their own. They can run some automated tests during the night or 24/7 if they want. So every time they change the code, they can check with the simulator if this code still works or if there's an error inside of it. Typically also with a real device, you cannot do all the kind of edge cases. So it's not really desirable to crash a robot into the wall to see if you detect a crash, but then you would do this kind of scenarios with simulators to simulate all these kind of errors, problems with the device. What's also interesting is that these simulators, because we're testing a medical system with them, we have to validate them. So we have to even test the simulators so that we can prove that they behave correctly, and then prove that if we run tests with them, that they can kind of be representable. So this is an interesting part, that not only the medical system itself has to be developed, according to some processes and standards, but also when you develop a simulator, you have to show that it works correctly. Okay, now we come to the demonstration part. So as mentioned, my colleague Christian will show a live demo of a typical treatment. Of course, he's not in a hospital running with real patient and the system, so he has it installed on his laptop. And you will also notice that from time to time, he will use simulators in order to advance to further steps in the workflow. So he doesn't have a real accelerator in the room, but he will use simulators when showing the demonstration. So Christian, if you're ready, I will disable screen sharing, and then you can take over. And yes.
Okay. Yeah. Hello, everyone. So as already mentioned, here I have our treatment control system that is running on my laptop. And I have also another GUI here that is used to control the simulators that we will use for this demo. And And as also was already mentioned, so treatment control system is basically a piece of software that connects various other subsystems from the, let's say, proton therapy facility to work together and allow the radiotherapists to perform the clinical workflow in a safe manner. So the GUI window that we are currently looking at is a GUI window that is usually installed and running somewhere in the control room of proton therapy facility. So yeah, this example that we will look at now is particularly for proton therapy case. Yeah, first step is obvious. So we need to make sure that only people with sufficient trainings and credentials are using the software. So we first require to enter user credentials. And here you can see that user is able to select various modes. The most obvious one is treatment mode that is used to perform the treatment. Besides that, we also support simulation, so to execute everything without delivery that is used to simulate the treatment, to present to patient, for example, how things will look like when the actual delivery will happen. And we also support various QA modes that are used for quality assurance and maintenance and so on. So for this demo, let's use the treatment mode, which is the most interesting one. So now we logged in the treatment control system, and the first step that happened at this point was that TCS connected to the oncology information system and obtained scheduled treatment sessions. And at this step, okay, we have the patient. The patient is already in the treatment room. And the responsibility of radiotherapists at this step is to select appropriate treatment session. So let's do it now and confirm that patient identity was verified. And now we open the session. So at this step, the TCS parsed treatment plan that was provided in DICOM format and displayed it here on the user interface. So let's take a quick tour through the GUI. So we have several main tabs. So the first one is setup. Here there are instructions how to position the patient on the table. So which immobilization devices to use and how. We have images and we have notes. Then the second tab is used to perform the motion. There are several moving parts of the system. For example, couch, gantry extension, and so on. And this tab is useful for positioning. We have delivery tab that is currently disabled because at this point, workflow does not allow any delivery of the dose yet, but we will see this tab later. And here we have reporting tab that is used at the end, usually to generate treatment reports and send it back to the oncology information system. The TCS also guides user through the workflow. Here are some instructions, high-level instructions, what to do next. Here are various statuses, which conditions that are required to the process are satisfied, which not. We have some patient information here and also a list of beams. So the treatment session is usually split into several beams, and each beam is used to deliver, let's say, one isocenter dose to, let's say, one isocenter in the patient or from different angle and so on. And for this treatment plan, is made of 4 beams, but for demonstration purposes, if you would want to fully treat the patient from full treatment plan, we would need to deliver all of them. But for this demo, let's deliver just one of them. So let's pick beam 2, and we will open it now. And yeah, at this point, let's say we have the patient already positioned and on the patient table. And the next step now will be to to go to positioning tab, and we will move the couch into the imaging position. We will do this by using two steps. We will use TCS to schedule the movement, and then we will use the hand pendant, that is basically a remote controller for the system to actually execute it. So I will press two buttons. So first one on the TCS to schedule the movement, and then actually two on the hand pendant to perform the movement. So now you can see that the couch successfully moved to the inside of on the imaging position. That is usually, for example, inside of the CT scanner. Movement was of course very quick because we used simulator. Usually it takes longer. And now we are ready to. Okay. Now we follow instructions. So the TCS suggests us to secure the room. So at this point, we will perform CT imaging, and at this point is recommended that nobody is in the facility that should not supposed to be there. And part of procedure is to make sure that this is the case. And it usually looks like that radiotherapists or some technicians go through the facility, through the accelerator area, to the treatment room, seek for hidden corners, and is pressing some buttons to confirm, buttons on the walls to confirm that nobody is in the facility. And this process is usually guided by the safety system. And at the end, when this procedure is finished, so room is secured, the safety system informs the TCS that room is secured. But for this purpose, I will just simulate the safety system. So we'll just press the button, and now everything is secured and we are ready to acquire CT image. The reason for acquiring CT image is the following. So we are currently using the treatment plan that was generated based on some so-called primary CT image. After that, we position the patient to the table as precise as we were able to. And now we will acquire another CT image, and we will use so-called secondary CT image. And we will use another piece of software called image registration software that will compare those two images and calculate offset between them. And this offset between those two images is called correction vector. For this purpose, we have another product that is called Position One and could be used, but it is out scope of this demo. So let's just simulate it. So now I'll use simulator to perform to first acquire CT image and then to obtain correction vector and send correction vector to the TCS. So now all those steps happened, were simulated, and as you can see, we got correction vector displayed on the GUI. And at this point, the radiotherapist takes looks at the numbers, and we can see that we are quite close to the primary image, so less than a centimeter away. We apply this correction vector. And from this point onwards, all future positions of the couch will be corrected for this correction vector. Okay, and now let's follow further instructions. So the next instruction is move to the treatment position. Now we will move all three subsystems that can be moved into the treatment position. So I will select treatment position for the couch. Now the patient couch is on the treatment position. The next step is to move the gantry. So this is rotating beamline through the room, across the room, and select treatment position, perform movement with the hand pendant. And now also the gantry is in the treatment position. And the third moving part in this example is snout. This is basically extension of the gantry. So we will move nozzle closer to the patient. And so I will select treatment position also for this one, press buttons on the hand pendant, and we are there. As you can see, the next step is correct or override patient position. So in real case, of course, position is never completely the same as ideal one. And as you can see for couch, there are certain offsets. And basically we need, at this point, we need to agree. So the radiotherapist needs to take a look at this number and confirm that this result is still okay. This result is usually all consequence of image correction, image registration. So we will just be happy with this result and we will confirm that everything is as it should be. And now, as you can see on the GUI, we are ready to request the beam. So we will now, I will press the button request beam, and we will send command to request the beam to the accelerator. So let's do it. And now accelerator approved that we got the beam. So this is usually, of course, not done immediately because, for example, there can be one accelerator and several treatment beams, and one treatment beam need to wait for another treatment beam to finish. And now we have beam available, and we will use some hardware button on the treatment console that is usually also located in the control room to turn the beam on. And now the coolest part of the demo, we are performing the delivery of the dose. As you can see, we are irradiating the tumor that is split into layers, and we are irradiating layer by layer and point by point. And TCS at this point does not control everything. The delivery of the dose is responsibility of the delivery system. TCS just monitors execution, so that the radiotherapist is able to monitor it. Okay, delivery is finished for this beam. There is some key switch to turn back from treat to prep. And if we follow instructions that are provided by the TCS, now we are ready to close the beam. And as you can see here, one of those 4 beams that we delivered is marked as completed. Of course, if we would want to do the full session, we would need to deliver all those beams, but it would not be so interesting because we would just be repeating the steps. So let's generate the report and finish the session. So here I'm able to enter some notes, and now I will send a treatment record to the oncology information system. Of course, we have warning that because there are beams that we skipped, which is okay in this case. Close the session. Okay, so this is consequence of at this point request is sent to user credentials server. That is okay, it succeeded. We sent request to confirm user credentials to user credentials server that is installed somewhere in our headquarters. But due to some problems with internet connection, I had to repeat several times. But yeah, so now we are back on the initial page. So we have one treatment plan less here on the list. And at this point, we are able to accept new patient and repeat the process. So yeah, this is the demo. So Luca, I'm giving a word back to you.
All right, thank you, Christian, for the nice demo. Let's go back to the presentation. Can you see the PowerPoint?
Yes, we can.
All right. We have only a few more slides, so I think 3. So yeah, Christian has showed you a demonstration of a treatment control system. So this is, I would say, probably one of the more complex parts that kind of helps with execution of the treatment. So, and also has probably the most source code or the most amount of code from the systems that we were looking at on our diagrams. Now, depending on which part of the software you're implementing, whether it's more of a higher layer or higher tier, as we saw, like you want to implement a graphical user interface, or you want to implement the logic that defines the steps of the treatment workflow, then there we typically use a more higher level programming language. And there, what's important and we really try to strive for is to use, modern or state-of-the-art kind of different design patterns or programming patterns. Of course, good object-oriented design is crucial. And you can imagine that then when you have multiple developers working on this source code, it really helps if it's then readable, maintainable, so that that you can work with different people on the same code base. Now, on the other hand, if we talk about the lower level of systems or software dealing or communicating directly with the hardware, there typically we have some lower level languages, even in some cases, then it's even almost hardware or hardware chips. There, the code, of course, it's a bit more rudimentary or sometimes harder to read, but that's the kind of consequence that you have to take if you want to have a more kind of real-time or deterministic or type of behavior. During development of such a system, and even later on, once it's in clinical use, of course, you encounter different bugs or problems with the system. So it's really important, and we have, kind of found that out, through our own experience, that we really have to have very good logging system. So anytime something doesn't work as expected, you might, get a report from the hospital that something doesn't work. A good logging system really helps us to, go through this telemetry and the different timestamps and find out what was happening when they were using the system, and then find out at which step, things broke and what was the reason for it. So this diagnostics is really, really useful then for the developers and fixing of the bugs. One thing that we currently don't have yet implemented, but we're kind of entertaining to have that in the future, is that using logs that are normally produced by the system, we could actually analyze how much different steps in the workflow take. So we could be able to see how much time the software takes, to process certain information, how much the RTT takes to prepare something and advance to the next step, how much time some hardware takes to respond. And based on that, we could, offer or suggest some optimizations either in the software itself or even to the clinical users, to tell them, hey, this is kind of the breakdown of your treatment time. Altogether it took 20 minutes, but out of that 10 minutes was used for, this step. So maybe you can look into it, how to make it maybe shorter, and then the overall treatment time would be shorter, and you could have more patients treated. Okay. Yeah, again, going back to the most complex medical device in the world, which proton therapy, carbon ion therapy, and similar systems are, this means that we have to comply with the regulatory requirements and standards. I think that this week you already listened to a lecture from Mohammed from Mid-Austron talking about the certification of such a facility, which is quite a big challenge. So already from the start of the development of software until the end, when it has to be tested, so verified, validated, we have to do it according to the requirements of the standards and regulations. So it's not just sitting down behind a computer and writing the code, doing the implementation, but there's a lot more, thinking about what do the users actually need, or how will we test the whole system. There's a lot of emphasis on risk management. So we sit down together with the team and we do that, maybe 50 times during the year. so every week, for example, and we try to figure out, okay, what can break, or how can the software maybe, do an incorrect calculation. And then we identify these risks, and then we try to figure out how can we avoid this risk or minimize it. So this is a really important part to make a safe system at the end, because we're treating people, patients. And yeah, at the end, if this machine or this software runs in Europe or versus United States, there are also certain details that are different. So depending on the final hospital where they are located, we have to take into account their specific regulatory requirements and make sure that the software complies with them. Okay. And yeah, just to give you also kind of a insight into how big this development is at the end. So for developing a system such as a treatment control system from scratch, from having nothing to having a working and tested product, it takes us approximately 4 calendar years, and there are around 40 different people involved in this development. So not all the time, not for the duration of all 4 years, but spread out over time. So you have different system engineers helping with requirements, with test cases. You have developers implementing the code, testers who test the code, project managers to make sure that everything will be done, according to some milestones and so on. So yeah, it's a really big challenge. And even having then the product available, a software, you still have to adapt it then to the final system. So as mentioned previously, some hospital might have a different type of robot, or they might have 3 treatment rooms, or some of them have cyclotrons, others have synchrotrons. So the software still has to be customized or adapted to that particular site. And that's again a bit smaller project, but still it can take 5 to 10 people, different people, between 1 or 2 years to adapt it to that type of machine. And then here I also put actually photos from one of the on-site visits, because I want to show you that going on site, to the hospital and then getting access to the hardware at the end is very important. So even though we have very good simulators and we can run all the tests, on our laptops, at the end, everything has to work with real hardware. So then we have a lot of travel to different sites, to different continents, and work with real devices. So that's also then kind of the fun part, going there with the team and seeing how the software then works with a real working system. All right. Yeah, this concludes the presentation. So thank you very much for your attention. And yeah, at this point, I would like to invite you if you have any questions for us.
Thank you so much, Luca. That was very interesting indeed. So do I have any questions from the students? Kristaps, are you managing this?
Yeah, I can manage it. I don't see questions. Oh yeah, there's one question now in chat. So Valerie says, interesting talk. I have a question about the validation of a simulator. What is the typical procedure for that validation? Thank you.
All right. So a good question. The simulators, what is a typical procedure would be, you need to write requirements for your simulator. So you need to have a kind of a written statement or a document specifying what you expect from the simulator, what it should do. Then you implement it, you make it, you develop it. And then you have to have a test plan and test report where you show that you have verified that the simulator now actually fulfills those requirements and that it behaves in the way that you wrote it in your requirements. So as the most basic thing is, yeah, you need to have requirements, test cases, and then a test report showing that your simulator behaves as expected. And that serves then as a validation report of your simulator that then typically you would show either to the regulatory body, so while certifying the machine at the end, or you might get asked every year. For example, our company gets audited because we have this ISO 13485 quality management system for development of medical devices. This means that every year, we get a visit of different auditors, and they would make sure, or ask us, how are you developing the system, or how did you validate this simulator? And then we would have to show them these documents, open them up, and they would inspect them and see if they are satisfactory.
Thank you. I guess that answers a question from Olivia. Okay, we have a question from Nicholas, but before that, I think I have a small question myself. It's maybe not totally related to, it was just interesting for me when you showed the simulation and sort of the spot scanning sequence, like the way how it moves from one spot to another spot. This sequence, how we move from one spot to another spot, is it something depending on the accelerator or the whole device that we use, or is it something that like the planning physicist specified?
Good question. So I myself I was not involved in development of the scanning system itself, but I know, so for sure it has to be predefined, so you cannot switch it from treatment to treatment. So the scanning pattern or the sequence is kind of then static. But I do believe that it comes already from the treatment plan. So the sequence of spots defined in the treatment plan is then followed also by the scanning system. Christian, do you have any more information?
Yes, confirming. So the way how to deliver the dose is provided in the treatment plan. So it's generated by the treatment planning software, and treatment plan consists of a list of layers, and for each layer we have defined energy of the beam, and each layer is split into spots, and each spot has defined coordinates X and Y. And yeah, we are moving through the layers by changing energy of the beam, and we are moving through the spots, so in X and Y, by using magnets in the nozzle.
And then there are even different strategies how you move between the spots. You might have continuous movement or continuous scanning without shutting off the beam in between the two spots, or you might actually finish one spot, shut down the beam, move to the next one, and then continue irradiation. And these, depending on which strategy to take, this is a decision that then the clinical personnel, they take, and they decide which one they want to use.
Thank you. Okay, we have questions from Nicholas and Adam, and we start with Adam, and then we move to you, Nicholas.
Hi, thanks both for such an interesting summary of this work, this product. You showed us a lot of the front end, where it's like for a user to actually get hands-on with it. What's the documentation like? If I say we're joining a facility, how would I learn it? Or if I forgot how to use something, how would I remember it? What's the documentation like?
Mm-hmm. Yeah, there are actually, so I can summarize it as there's a lot of documentation behind. I think for like a treatment control system, there are in the range of 70 different documents. And specifically, you're asking about how do you remember certain things. We can talk about in different aspects of documentation. Some of the documentation is more on the level of developers. So for example, architecture or detailed design would contain diagrams similar to the ones that we were seeing today, plus a lot of text describing each box, each arrow, the type of protocol that they use to communicate between each other. So they would go into all the details there. But then in addition, you would have then the user manual. That one would be intended for RTTs, so the clinical personnel, how they use the system through the GUI. You also have the installation manual meant for some service engineers or engineers installing the system and configuring it. So yeah, then at the end you have different kind of manuals plus design documents meant for different people that they know how to develop the system, plus later on If you want to change it, maybe you want to add new features, you go back to that document, remember things, and then change it.
Okay, since I don't see anything in any of the chats and no other hands raised, Nicholas, you're welcome.
Thank you. You know, a textbook case of engineering, especially when one looks at safety, is the TERAC 25 accident, which basically was due to the overdosing of radiation therapy machine, the TERAC 25, in fact, that finally gave the dose of about 125 times the prescribed dose to patients. And in fact, there were 6 deaths resulting in the accident. This was in 1980s, mid 80s. And in the beginning, the company didn't admit that there was a problem with the machine and they attributed it to human error. But after a few years, there were 2 engineers who decided to lock themselves in the radiation control, well, in the control room of a machine until they figured out exactly what had happened. And your presentation, in fact, reminded me of this accident because, of course, one has to look at the safety precautions that are taken when designing such machines. And this is especially important for machines that are used for treatment. So my question, in fact, is this. This is like a textbook case. And ultimately, it turned out that they were using recycled software of another machine. The code was very difficult to debug at the time. That was debugged in assembly code. So it was very difficult, in fact, to program in assembly. For those of you who have programmed in assembly, you know how it is at machine level, so it is very low level. And it turned out that there was an intern who was tasked in doing some routine, and there was a bug in the logic. Of course, it's not the intern's fault. You don't put an intern on something that is safety sensitive. My question is this: when it comes to safety, how much can we rely on software, especially given that we have many states of the machine? And how does software actually marry with hardware to avoid certain safety accidents? So I imagine that there would be a number of safety features in software, but how then is that enough, or should there also be a number of hardware-based systems whereby, for example, there would be a sensor that is not linked to any software whatsoever, that would just burn out a fuse in case, for example, an unlikely situation happens where a very high dose is detected very quickly, as a last safety catch. And there are many other examples of safety, of accidents that resulted due to software or some operating system that was not real time, but was used as real time, for example. Right. But this is a textbook case that is very topical because it is, of course, related to radiation and therapy. Can you comment on this?
Yeah, sure. A good challenging question, and I like it because a simple answer is we do not want to, or nobody should rely completely on software when it comes to making sure that things are safe. So that's a simple answer. Then a longer answer is, let me go back to this diagram and let's just take this away first. Here, I want to point out this part and also this part, for example. These two are typically hardware-based systems. So, of course, TCS would load the treatment plan into these systems, but then once you start the irradiation, safety system plus the dose delivery are completely independent. Even if TCS crashes, for example, these two would monitor if the doors are open or closed, what's the currently delivered dose, is it already has reached the prescribed level or not. And they inside even then have, redundant 2 ionization chambers, just in case one would give erroneous feedback. They have 2 either CPUs or 2 chips that, kind of monitor everything. So this is kind of a simple answer. So when it comes to real-time delivery of the dose or even motion, you don't want to rely on this particularly high-level software, but you want to do it with hardware devices on a lower level. And also a good pointing out of TERAC 25. I think this is a good, kind of a textbook example. We actually had a dedicated session inside within Cozy Lab to discuss it. And then every few years, we try to remind new people, new employees about it. Hey, you should read this white paper. It's very insightful, to think about the risks.
Thank you, Luca. Are there any other questions?
Not that I see. Both chats are empty, and I don't see any raised hands. So, if anyone has any questions, then now would be the time.
All right. I think we can stop here. It's 3 o'clock. Luca, thank you so